Hello everyone, Professor Dustin here, and in this video I'm going to introduce the double slit experiment, which is an example of interference. So now that you've talked a little bit and seen some videos about the interference patterns that waves can have when they add together, superpose, they can either interfere constructively and get bigger, or they can interfere destructively and get smaller. So the double slit is a classic experiment. It's got a lot of applications in physics. The one application we're going to talk about in this class is how you can use the double slit experiment to create two single sources of light, which you can then use to interfere with each other to study the phenomenon of interference. So first thing I'm going to do is just set up the experiment, which is the way to create two little point sources of light for the purpose of getting them to interfere with each other. So the setup for this experiment is you start with a slit, actually two slits, a pair of slits separated by some very small distance, and then you shine light onto the slits. The light passes through the slits and then falls onto the screen, and then you look at the pattern formed on the screen to try to understand where the interference and where the constructive interference and the destructive interference pattern happens. So to see how that happens, just imagine as the two sources of light, as light comes through the double slits, it's kind of creating 2 point sources. So from the 2 point sources are going to be rays of light that shine out from the slits and then fall on the screen. So let's pick a specific place on the screen. Let's just say like right there, and look at where the sources of light from each of those slits comes from. Well, one of them obviously comes from the bottom one, and then one of them comes from the top one. And if you imagine the light that's coming through one of these slits, it's waving, and it hits the screen, and then this one is waving, it's waving, hitting the screen. But what happens, because the distances the light travels are different, specifically the bottom one is longer, they end at the screen maybe out of phase or at a little different phase than when they started. So when they started, they came from the same source, so the light sources were in phase. But when they travel a certain distance, since the distance is different, they'll be shifted off from each other. So for example, one might fall on the screen like that, and the other, if it's shifted by the right amount, might fall on the screen like this. And that's destructive interference. You add up those two waves, they cancel each other. Now, of course, what's really going to happen is they're going to be offset by some small amount, like that. And you'll get like some partially cancellation of the interference pattern. So what we're going to ask is, under what conditions do we get a complete summing of the waves? When do the two sources of light create waves that are exactly in phase right there? So when they're exactly in phase, that's constructive interference. So when do we find that they have exactly constructive interference? So the way we're going to do that is we're going to measure the lengths that each ray of light travels. The first thing we're going to do is we're going to say, okay, this is some kind of triangle, so we can figure out how far each of the distance between the slit and the screen in each case. In fact, what we're going to do is we're going to say, well, actually, if that's one distance, that distance is found right here as well. So let's start out by drawing a little triangle like that. Let's do a different color. Right there. And say this is an equilateral triangle because it's equilateral, these two lengths will be the same, and therefore the only thing that we're going to have to look for is this extra difference, right? If the two path lengths from there to there are the same because they're an equilateral triangle, then the difference between the light paths is this little distance in there. That's called the path light difference. So that path light difference is going to tell us if the two waves are synced up or not. Okay, so to determine what that path length difference, to determine if the waves are synced up or not, we're going to make some assumptions. The first assumption we're going to make is actually that and I'm going to draw this a little bit bigger, we're going to say the interior angles right there are actually 90 degrees. So now, of course, that's not true, because if those two were 90 degrees, then this wouldn't be an equilateral triangle. It wouldn't be a triangle at all. But this is called the small angle approximation. If the screen is far enough away from the slits, then we can indeed assume that those two angles right there and right there are actually 90 degrees. That's going to make our calculations way easier. So the next thing I'm going to do is I'm just going to blow up that little triangle into a big triangle, so then we can see what it actually looks like. Those are the two sources of light going out towards the screen. Okay, so this is the blow up of that triangle. What we want to find is we want to find the path length difference. In particular, what conditions should the path length difference have? Well, the path length difference, for instance, if we want to have constructive interference, that path length difference should be some multiple of the wavelength, right? So if the wavelength is 3 meters, the wavelength between successive crests is 3 meters. If this path length is exactly 3 meters, it means that the next wave that comes along is 3 meters behind that one. But if it's exactly 3 meters behind, it's going to be, if that's also exactly 3 meters, then they're going to sync up and they're going to be in sync with each other, right? So we want this path length difference to be some multiple of the wavelength, some integer multiple of the wavelength, where n is an integer. 1, 2, 3, 4, 5, because if it's 1, 2, 3, 4, 5, then this path length difference will ensure that our waves sync up when they reach the screen. Well, how are we going to calculate this path length difference? We're going to explore the geometry of this triangle and how it relates to the geometry of the situation to get the conditions upon which we can actually get constructive interference. So specifically, this d right here is the distance between the slits. That's a fundamental parameter that we know. We've created the slits with some distance, and so we know that. In addition, the distance, the angle at which the light is traveling, that's another sort of fundamental parameter. That tells us where on the screen the image is being formed. And so if we drop a perpendicular there and call that angle theta, that angle theta will tell us where on the screen the light from those two slits, like at exactly that point, if that's going to be constructive or not. But that angle right there is also this angle right here inside the little triangle with our path length difference. The easiest way to see that that triangle and that triangle are the same are with your mind. Imagine what would happen if both of those triangles went to 0. Specifically, take this guy. If that triangle went to 0, the light would be hitting the screen more straight on. And that's exactly what would happen if this triangle went to 0. If that triangle went to 0, this light would be going directly onto the screen straight. So therefore, that angle and that angle must be exactly the same. There's other ways you can prove it. For instance, this horizontal line right here is equal to a horizontal line right here. And so the angle between that and there, you could show that that's equal to that angle. But this is, I think, the most direct way. Okay, actually, that's pretty much all it, right? So now in this little triangle, if I want to know how much the path length difference has to be in order to equal n lambda, well, that's just some trig function related to the distance between the slits. And actually, you can see that, since I said these guys are right angles, those who are right angles, that means that this guy is a right angle. So I've got a nice right triangle there. That is the opposite of that angle. So the condition here for the path length difference, the actual length of that is going to be d sine theta. So the condition for constructive interference is d sine theta is n times lambda for any n. So what this looks like, I'm going to draw a picture of what it looks like on the screen here. When n is 0, that means the path length difference is 0. That means that the length from the two sources is exactly the same, and that's falling right at the center. So right there, you have a bright peak. So your brightest peak is always right at the center, because that is definitely constructive interference. As you get further and further away, you start to destructively interfere with each other, and the waves start to overlap a little bit, and the light drops. But then at some point, you kind of pass the halfway point, and the light starts to constructively interfere again. And at some point, you get a peak in that constructive interference. That's exactly n equals 1. So n equals 0. Sorry, n equals 0. N equals 1, and you get one of those on either side. I'm going to try to put it right where I calculated it before. But then as n equals 1 gets, as you get past n equals 1 to 1.1 or 1.2, they start to destructively interfere again, and you get less light coming through on the screen. And again, as you continue to the n equals 2, and the n equals 3, and so on and so forth, you get an infinite series of these interference lines. Now, typically, they do get dimmer and dimmer as you go. That's because more and more of the light is less and less concentrated, because as you go over here, there's an angle here, which means that the light is actually becoming less and less concentrated as you get further and further away from the center where it's brightest. But you do indeed get this n equals 1, n equals 2 conditions. So the last set of parameters we want to talk about is actually the parameters related to the screen. So this d sine theta equals n lambda, that's the size of the slit and the angle that the light passes through the slit. But that doesn't really tell you like where on the slit the maximum are going to fall. So in order to do that, we have to like add a coordinate to the screen, call that like y or something, and then determine the distance from the slit to the screen, and I'm going to call that big D. That distance is going to be big D. And you can see that because of this triangle that we have in here, the distance between the center and where the maximum is, where whatever the point is on the screen we're looking at, that's y. And so this is forming another right triangle. And actually, that triangle is satisfied by sine theta is opposite, which is the y, over the distance d. So you can actually see that the sine theta is seen in both of these things. This is the condition for constructive interference. This is just the geometry of the screen and the slits. So you can just replace the signs in there with y over d to get dy over big D equals n lambda. And this is probably the most direct way to use this formula. For instance, if we wanted to know where on the screen the maximum lie, we could solve for y and write this as big D over the slit distance d n times lambda, where y, when n equals 1, the y position is 1, so d over d times lambda. When n equals 2, you put a 2 there, d over d equals 2 times lambda, and so you can get all the positions on the screen using this formula. So this is the key sort of formula for the double slit experiment, is this d sine theta equals n lambda. This folds in the distance of the slits to the screen to allow you to predict where on the screen the actual interference pattern is going to lie. Okay, great. Hope that was a good introduction to this. It's a pretty simple idea. The end result is just this, but it's important to kind of know where it comes from. Why do we have these interference patterns in the first place? It's because the light from the two different slits are traveling different distances. So as one travels a little bit further than the other, you get constructive or destructive interference, and you can predict where the constructive ones happen, at least, just by using a simple equation like this and putting in integers for the n values. For d sine theta equals some n integer values times lambda. Okay, great. So we're going to do some work on this in class. Thanks for watching, and I will see you in class.